last lesson of our unit, and it's called Working with Time. So what we're going to be doing here is we're actually going to be converting equations to different time periods. Here it says the exponential functions we have been working with always need a clearly defined amount of time for t. For example, t is often defined in years. Sometimes it is helpful to convert to a different unit of time. To convert from one time period to another, use an exponent because the time is in the exponent for exponential functions. Showing a rate for a different time period is not the same as compounding periodically. So it's going to feel like it because those questions say like 6% a year compounded monthly. So we see the word years and months in the same problem, but this is going to be a different type of thing where they actually want me to convert the equation to show something for a different time period. So if you don't see this word, you're not compounding periodically. So let's look at our first question. The population of bats in a large cave is 340 and is growing exponentially at 17% per year. So notice first off, we don't have any compounding. There's nothing continuously. We don't see that word. So this is just our basic formula. So we're going to start out and write a function to represent the population of the bats after t years. So this is just our basic formula. And I'm actually going to do the steps down here because I also have steps written. So I'm going to write the work down here with my steps. So the first thing we're doing is we're writing a basic exponential equation using the unit of time given with a percent change. So that's years here. Right. So this is our basic equation is P times 1 plus R. So that's 1 plus 0.17 to the t. Now this question, if we read the rest of this sentence, it says where the monthly rate of change can be found from a constant in the function. So that sounds a little tricky. So right now, what constant they're talking about is basically this b value, right? That's what reveals the change. So 340 is just the start value. Right now, my base reveals the yearly change of 17%. We want to change it to the monthly change. So we're going to determine what you would multiply by to go from the starting unit of time. So our starting unit of time is years. And we want to go to what the question is asking for. So the question is asking for the monthly rate. So we're trying to go from years to months. So that's getting smaller. So we want to multiply by a fraction less than 1. And that fraction we would multiply by is 1/12. So we're going to use that multiplier, the 1/12, as the exponent for the current base. Okay, so we're going to take this 1.17 and raise it to the 1/12 power. So I'm going to move this down just a little bit so I have room. So here's my a of t. And I'm going to raise 1.17 to the 1/12. Okay. So now that's not really legal because I can't just change the equation, right? So if I'm going to put a 1/12 with the 1.17, because the equation needs to be equivalent to the original, write the reciprocal exponent with t. So if I'm going to put a 1/12 in there, I'm going to have to put a 12 on the outside. So basically, these two blue parts, the 1/12 and the 12, we could cancel them out and go back to the original equation, okay? So this is just rewriting it. If I type in this, that is going to reveal the monthly growth rate. We're changing the base to be a base for months. So basically, the 340 stays. I'm going to type in 1.17 to the 1/12. And that's going to give me 1.0132 to 4 decimal places as the problem suggested. And then that 12t stays on the outside. So this is no longer a times b to the t, but we are revealing the monthly growth rate by changing that base to a base in terms of months. So that's the formula we're going to write up here for f of t, the formula that reveals the monthly growth rate. So that's 1.0132 to the 12t. That's growth, right? And what percent are we increasing per month? We would just do 1.0132 minus 1. And we want 100th%, which is why we set up with the 4 decimal places. So if I move this over 2, we're increasing by 1.32% per month. Now, just quickly, if we had done 17 divided by 12, it would be kind of close to 1.32, but it wouldn't be exact. And that's because percents don't work by multiplying, they work with exponents. Okay, and that's why we have to do the problem in this other way. So let's look at some more. So here's another one. It says the value of a brand new car is $28,000 and the value depreciates 19% every year. Write a function to represent the value of the car after t years, so the variable is still years, which is why we have to kind of convert things, where the quarterly rate of change can be found from a constant in the function. So we start out with our basic function. This is decay, right? So I'm going to do this up here, 1 minus 0.19, or we have to subtract because the R value is negative 0.19, is going to be 0.81. So that's what I'm going to put here. I'm going to leave a little space because I need to convert to the t. And I'm also going to move my t over because I need to leave a space there too, we know. So if I want to go from t's in years to a quarter, right, I would multiply by 1/4. So I'm trying to change the 0.81, which shows the yearly decay rate, changing it to a quarterly decay rate. So I'm going to raise that to the 1/4. And then to balance it out, I need a 4 out here. Okay. So I'm going to type this in my calculator to get that base that reveals the quarterly growth rate or decay rate. Okay, so if I type that in, that is going to give me, over to the right page because I can't do this up in my head. Not the right page still. There we go. 0.9487. Okay, and we have out here the 4t. So on delta math, I'm not going to rewrite it, but that's what I would put up here. Okay, this is decay. So this is kind of similar to the problems from the last lesson where those two change together. Now to find the percent it's decaying by, we have to do the 1 minus 0.9487, which is going to give us 0.0513. So this is 5.13% decrease per quarter, okay? So basically, as I said, it's not exactly 19 divided by 4 because that would be smaller than 5, okay? It works a little differently because we're changing with the exponents. So one more problem, and then we actually have one more that's not a delta math, just to kind of show you a different take on these problems. In a laboratory experiment, the population of bacteria in a petri dish started off at 400 and is growing exponentially at 8% per hour. So this one's a little different because t is in hours, okay? So let's write that function first. Growing at 8%. Now we want to write a function to represent the population of bacteria after t hours, where the rate of change per minute can be found from a constant in the function, okay? So I'm going to set this up. We know we have to change our function, so we're going to leave some spaces. So we are now going from hours to minutes. So that's getting smaller again. So this is 1/60th. So I'm going to raise this to the 1/60th, put the 60 out here. So once I take this in, okay, it's going to be pretty close to 1 because if it's growing 8% in an hour, it's not growing so much each minute. So this is going to be 1.0013 to the 60t, 400 in the front. Okay, So that's my function, and really I'm writing a of t, but all these are f of t, right? Hopefully we're okay, right? That's kind of the same thing there. Now this is growth, not very much growth per minute, but if I subtract, right, move the decimal over 2, that's 0.13%. So that's what I would put right there in that spot. So one more on the next page. And I purposely included this one because all the ones on Delta Math, the time period's getting smaller. I wanted to show you can go in the opposite direction, and this is also a different type of problem where you already have the equation. So this says the cost of a microwave m months after it was purchased can be modeled by this function. Write a function d of m, which reveals the yearly decay rate of the microwave. So this is the monthly decay rate, and this should really say, now that I read it, the cost of the microwave, because the microwave itself is not decaying, right? So here we have C of m. It shows a monthly base. So we're going to make D of m, and we could still call it C of m, but I'm calling it a new equation now. Now the variable needs to stay months. So I'm making those spaces so we can still have m for months in here, but it's going to reveal the yearly decay rate. So this is going from months to years. So now we're getting bigger, so the exponent is 12. So that means I need to put a 12 in here, and the 1/12 is going to have to go out there, okay? So when we write our equation, d of m, if I type the 0.9916 to the 12th, that is going to give me 0.9037, okay? And then we have our 1/12 m out here. Now that's all we have to do. We don't have to find a percent or anything. It's just write d of m. So that's your answer. So I just wanted to show one where we went from a smaller time period to a bigger time period. Basically, we end up usually with a whole number inside and then the fraction on the outside.